This is a video for notes for section 3.4. This is two more rules that we'll use all the time from now until the end of the year. These will be things that we do all the time. Same as once you use multiplication, that really never ever goes away in your math education, right? So the product and quotient rules. And since we're talking about rules for taking derivatives of functions, you might intuit that we're talking about here the product of two functions, and here this will be the quotient of two functions. I think what I'm going to do is prove one of them for you and just give you the other one. And if you're interested in the proof for the second one, the quotient rule, you can check out your book for that. But it's pretty similar, albeit a little bit more complicated than the first proof. And I might add here, I should have said this in the last video, that once you know one of these rules, although I do like you to see the proofs of them so you know why they work, you're not responsible for reproducing these proofs. You just need to know the rules. And I do not like to, like most math teachers, do not like to just give you facts without actually backing them up with some kind of logical argument. So I'm going to do that with this one, and then I'm going to be hypocritical, according to what I just said, and not give you the proof for this one, but it is in your book. Okay? So, consider a function, let's call it h of x, right? We usually use f, g, and h, that part of the alphabet, to name functions. I'm going to call the function here h of x. And let's say that that function is actually the product of two other functions. So if you're imagining, like, well, what would that look like? Well, you could think of an example. It could be something like this. Our h of x function could be like, it could be x cubed plus x times another function that might be, say, like x to the 1/2 minus 1. Now, of course, at this stage of the game, we're not really dealing with anything more than polynomials and relatively simple functions. Like, we haven't dealt with trig functions or logarithmic functions or exponential functions or any of that crazy stuff. So you could, of course, just FOIL this out, right, and then use rules from section 3.3 to find the derivative. But this will give us another way, and it will also give us another way, like in case we had something like h of x is equal to sine of x times the natural log of x. Now, of course, we don't know how to take the derivative of either one of those functions yet, so until we do, we'll have to put this rule on hold. But this rule will give us a way. If you know the derivative of this one and this one, you can find the derivative of the product. Well, isn't that easy? You're thinking, don't you just do this? Well, let me just make it very clear that you are not allowed to do this. You're not allowed to just say, well, the derivative of the h function would just be the derivative of that one times the derivative of this one, wouldn't it? Well, it sure would be nice if you could do that, but you can't. And it's not because the people who invented calculus were cruel people who wanted to continue the tradition of making things more difficult for you and you have to do math. It's because it just isn't this. And I think it's really easy to see why it's not. If we said, here's a real simple example, if f of x, let's say the h of x function, was the product of x times x, right? That's a very trivial example. And you think, well, why wouldn't you write x squared? Well, let's just say we happen to write it like that. Then if this worked, which it doesn't, would say that the derivative of that is equal to, what's the derivative of just x? Well, that's like 1x to the 1. So by the power rule, or if you just think of that as like x is like a line with a slope of 1, the derivative of x is just 1, and the derivative of that is 1. So then the derivative of that would just be 1 times 1, or 1. But this is the same as x squared, and we know that the derivative of x squared is 2x, not 1. So this is all no good. It does not work that way. So we have to find, if we want to have a general rule for doing this, we have to figure out what it is. And our recourse will always be, when we're trying to tackle some kind of new derivative situation, we always go back to the definition. So, if h of x is equal to f of x times g of x, then I'm just going to use the definition of the derivative. Then h prime of x is equal to, and now I think this would be like, well, I'll write out this step here. It would be like h of x plus h. Now, maybe this is a slightly unfortunate name I've chosen for the function. This is the tiny little h, and this h is the name of the function, right? Minus h of x. You understand what I'm saying there? This is the name of the function, and this is our little thing that's approaching 0. All right, almost forgot to write that again. Over h. And since the h of x function is really the product of these two, that means this really means, and now that our notation problem is going to go away, so I'm not going to call it that anymore. It's really f of x plus h times g x plus h minus f of x times g of x all over h. You might want to pause for a second and see how this turned into this, because that's what that function is. All right, so take a second to think about that. Okay, now this is the step in this proof that's the how would you ever possibly in a million years think to do that step. Well, some clever person a long, long time ago thought of, who probably had looked at this problem for a very long time, thought of doing this. So I'm just reproducing the standard way of proving this. So if it seems kind of mysterious why you would do that, then don't worry about that. This is just how we prove it. So the weird, mysterious thing I'm going to do is, in the middle of these two terms, I'm going to subtract and add the same thing. Now, if you just subtract subtract 2 and then add 2, you've effectively added 0 or not done anything, right? So you're allowed to do that. It's kind of a weird thing to do, but you are allowed to do that, of course, right? It's like adding 0. So we start with the first term here, f of x plus h times g of x plus h, and then the mysterious term that I'm going to both subtract and then add is that times the g function. Right? I'm going to subtract that. Notice that's not part of this, right? I'm adding something in here that wasn't there before. And to counteract the fact that I just subtracted that, I'm then going to add exactly the same thing. Right? So that keeps it all balanced out. Right? Like at the very beginning of the first Raiders of the Lost Ark, the first Indiana Jones movie, right? Where he's got the bag of sand and there's the golden head thing that he's trying to steal, and he grabs the golden head and he puts the sand there, right? Because he hopes that they weigh the same, so effectively nothing would happen. Of course, it didn't work out for him, but it's good here for us. Okay, so again, this in the middle here, this is just 0, right? So really I have the same, it's equal to what I started with. Again, you can scratch your head and wonder how anybody would ever think to do some crazy thing like that, but you'll see how it pays off in a minute. Okay, now I'm going to do a little bit of grouping of the terms and do a little bit of factoring. So here, these first two terms have an f of x plus h in common. So I'm going to go ahead and factor that out. All right, so if I factor the f of x plus h off those first two terms, that leaves behind g of x plus h minus g of x. And then if I look at the second two terms have a g of x in common. So I'm going to factor that out, and that leaves behind f of x plus h minus f of x. Okay, I'm just doing algebra here. right? Okay there? And then this is all over h. But of course, that's like a common denominator. If I wanted to, I could split that like this. Usually we take fractions and try to get a common denominator and put them together. So if you looked at these two and said, oh look, there's a common denominator, I can put them together. You could get to this step. So likewise, all these things are reversible. Here I'm trying to split it up and take advantage of the fact that if this is the denominator of the whole thing, I can write it as two separate fractions like that. Okay, now I want you to notice here that the limit as h approaches 0 of this, well, there's no problem here with this h just going to 0, right? That, as the limit as h approaches 0 affects this term, that just turns into f of x. And here, how about the limit as h approaches 0 of this expression? Well, hey, that looks kind of familiar. As h approaches 0, g of x plus h minus g of x over h, that's the definition of the derivative of the g function, right? Think about that for a second. That's the definition of the derivative, limit as h approaches 0, g of x plus h minus g of x over h. So I'm going to write that as that's the derivative of the g function. Plus, here, there's no h's at all in this piece, so that's just g of x times, and then look, the limit as h approaches 0 of this, that's the definition of the derivative of the f function. So, there you have it. That is the product rule. If you want to take the derivative of the product of two functions, this is how it works. You take the derivative of the second one and multiply it by the first, and then they trade roles here. When I do this, and if you want to be consistent with the way I'm going to do it in class and in examples and so on, I will always take the derivative of the first function first, then leave the second one alone, and then switch. So my operational way of doing this will be the reverse, but of course addition is commutative. So it doesn't matter the order that you do it in. Again, if you want your answers to always look like answers that I have in videos and that I do in class, then I'm actually going to do this term first. Okay, so let me show you how that works. So let's say we have f of x is equal to x squared plus 1 times the square root of x minus x. That's fine. Let's leave it like that. So if I treat this like the first function, and this one is like the second, this is like the product of two functions, right? Then the derivative of this product of two functions is the derivative of the first, which is 2x, right? You should have plenty of practice with that. I'm hoping that that's very clear now, right? That's not a hard problem. So the derivative of the first times the second one left alone plus the first one left alone times the derivative of the second. Now that's really x to the 1/2. So its derivative would be 1/2 x to the negative 1/2, and then the derivative of x is 1. Right? So when I go through the sort of rhythm of doing this, the way that I'll say this, I always say the derivative of the first times the second plus the first times the derivative of the second. Right? They each get a turn to be left alone and have their derivative taken. Right? This term is the taking the derivative of the first and leaving this alone, and then we leave the first alone and take the derivative of the second. That's how we use the product rule. We could try something like, oops, sorry, I can give you a function first. Let's say f of x is equal to, this will be a good one because we can then quickly check it by foiling. So let's say we had this. Now, if you had this function, you might just be tempted to FOIL that out and then take the derivative using the power rule. I think I'd be tempted to do that too, but we can do it using the product rule. And we should get the same thing, right? So here, notice that if I did FOIL this out, it would be what? 2x squared minus 9x minus 5, right? But I'm going to try taking the derivative, and then of course you could just take the derivative of this. It should just be, what, 4x minus 9. But let's try doing it using the product rule and see if we get the same thing. So the product rule says take the derivative of the first, which is 2, times the second, plus the first times the derivative of the second, which is just 1. Right? Derivative of that is 1, and that's 0. Okay, now that should be equal to this. I mean, our rule certainly has to support things that we already know are true. So 2x minus 10 plus 2x plus 1, and sure enough, that simplifies to 4x minus 9. Check. So you can, we could argue about which way is easier in this case, but it really doesn't matter. This is just an example that supports our rule, right, with other rules that we already knew. And in the future, there will be examples where you won't have another way of doing it, right? Okay, now, the quotient rule. This one I'm just going to give to you, and you can check out the proof in the book. It's got that same like mysterious add, subtract, some thing, and like magically things group into definitions of derivatives. It has a very similar feel. You can go through that in the book, and if you're really interested and you go through it in the book and you can't quite follow it, then just bring that to my attention and we can go through it together. So the quotient rule says this: if you have some function, I'm going to call it h of x again, that's equal to f of x over g of x, then the derivative, h prime of x, is equal to the function that's on the bottom times the derivative of the one that's on top minus the one that's on top times the derivative of the one that's on the bottom over the one that's on the bottom squared. Now that's definitely more complicated than the product rule, right? And certainly maybe a little bit more challenging to remember. And please note that because this is subtraction here, if you mix up the order that you're supposed to do this in, it will be incorrect, right? You'll have an answer that looks almost right, but it'll have the wrong sign. Now I'm going to tell you a little mnemonic device that I learned a long time ago when I learned how to do this. And it seems to work. It's just sort of a catchy way of remembering this. I'm going to call this low. I'm going to call that low because that refers to the function that's on the bottom. And then we're taking the derivative of this one, so I'm going to say d, and I'm going to call that the high one, right? This is the low and this is the high. And whenever I say d in front of something, that means you should be taking the derivative of that one. And then minus, this is high d, that's taking the derivative of the bottom one, and then over low, low. So this is the little mnemonic device. You sort of read through this. Low d high minus high d low over low low. Low d high minus high d low over low low. You have to absolutely remember to start with the low, right? Low d high minus high d low over low low. You want to probably say that to yourself about, I think the research says that about 30 times is what it takes to burn it into your brain. So go ahead and pause the video and say it 30 times. Are you back? Did you really pause and say it 30 times? I bet you didn't. I'll give you another chance. Pause. Okay, good job. Research also supports, I think, that if for people of exceptionally high IQs that you can actually get away with only saying it 20 times, but just in case you are overestimating your intelligence, I tell you that after you already did it 30 times, so we should be safe regardless. Okay, so how do you use this one? So let's do some examples. So let's say we've got a function here. F of x is equal to x squared minus 1 over x plus 2. Now here, we're in a different situation. Like, I think we really need this rule this time, right? Because I can't FOIL this out, right? And it doesn't factor and simplify, so I think I really do need some kind of rule. So let's see how it will work. So the quotient rule says the derivative of a quotient is low d high minus high d low over low low. So let's go through and see how that plays out here. So low d high minus high d low over low low. Right? So they're going to look like this, right? I'm telling you, the most common mistake that people make is to mix these up, right? I'm not even going to say, I'm even going to start saying it with that one first, because I want to get that in your into your brain. It's got to be low d high is the first term here. Now, how much simplifying do we have to do? Well, that's a good question. There's two answers to that. In general, if I gave you this problem and just asked you to come up with the answer, and it were like a free response question, then I would not make you simplify this. You could leave your answer like this and not take a chance making any algebra mistakes. But you will see plenty of, both in practice for homework and on quizzes and tests, you're going to see plenty of multiple choice problems. What does that mean? It means you need to simplify until your answer looks like the correct answer choice. So I think I'm going to let you decide how you want to deal with that, but at some point you're going to need to practice simplifying things like this and making sure that you don't, like for example here, this minus sign is going to distribute. People who are a little bit sloppy writing out their work and their steps are likely to make careless sign mistakes, and you can bet that the people who write calculus multiple choice questions for the College Board know the mistakes. They anticipate the careless mistakes that you're going to make, and the answer that results from making those careless mistakes, those answers are usually there among the choices. The distractors, as they're called. Did you know that? The wrong answers in multiple choice questions are called distractors. That's educational lingo. So you don't want to be distracted by them. You want to get the right answer. So I think probably you want to practice at least some of the time simplifying these things. Also, if you want your answer to, if you're doing odd numbered problems from the book and you want your answer to match up to the correct answer in the back of the book, they're probably going to have some simplified version of the answer, and it will be hard for you to tell looking at this and comparing to their answer if you're right without doing any simplification. So those are issues you're going to have to deal with. So on the one hand, I'm not going to make you simplify. On the other hand, in various contexts, I think you're kind of going to be forced to, whether I'm actually asking you to or not, right, just because of the nature of the question. So those are the quotient rule, that's the product rule and the quotient rule. You'll get to know them very well, and it's never optional whether you use these rules. If you've got a quotient, you must use the quotient rule to find the derivative. If you've got a product, you must use the product rule. Again, it's a rookie calculus mistake, careless mistake to want to say, don't write this down in your notes, I'm just going to show you something like to say, oh, f of x is equal to x squared over 3x plus 1. So let's see, the derivative of that is just, if I take the derivative, I'll just take the derivative of the top, and then I'll take the derivative of the bottom, and then I'm done. But this is not correct, right? If you want to find the derivative of this, it's a quotient, you must use the quotient rule, right? It's the same as that rookie algebra mistake, which I'm sure none of you ever make anymore, right? Which is if you were asked to simplify something like this, x plus 2 times x minus 3. You say, oh, let's see, x times x is x squared, and 2 times that, so that's x. So that's that, right? But no, it's not. You have to FOIL it out. Why do you have to FOIL it out? Because that results in an expression that's equivalent to this one. X squared minus 6 is not equal to this. It's not because Miss Seaman, for example, wanted to make up rules that made things more difficult for you. It's because foiling it out is the process that results in an expression that is, in fact, equivalent to this one. Likewise, for the product and quotient rule, those are the rules that you must use to get the correct derivative, right? It's not optional. So get used to those. This is not unlike pre-calculus where you learned something and then you kind of moved on and there was like a whole new topic going from, say, logarithms to like polar coordinates or something like that. They seem kind of unrelated. This is actually back more to like Algebra 2 might have felt, where every single time you learn something, you continued to use that skill in the subsequent chapters, the subsequent material that you were doing. That is absolutely the case here. The product rule and the quotient rule are going to be with us for the rest of the year. And even though you're learning it at the very beginning, just in the first few weeks of calculus, it's foundational stuff that is going to keep coming up over and over and over and over again. We're going to use them all the time, almost every day. Rarely will a day go by where we don't use one of those rules. So there you go. It's a motivational speech for you.